Welcome to Nexus Tech. You know, for years, quantum computing has always been the technology of someday. It's always been just around the corner. But what if someday just arrived? It really looks like a series of breakthroughs in late 2025 across hardware, software, and even investment suggests we finally hit a quantum tipping point. And that's exactly what we're breaking down in this explainer.
So let's just ask the big question right up front. Is the quantum age finally here? I mean, after decades of promises, this recent cascade of results, it really suggests we've hit a genuine turning point. So let's get into it and break down exactly what just happened.
All right, here's how we're going to tackle this. First, we'll look at the machines themselves, the actual hardware. Then, we'll get into the code that runs them. After that, we'll see how the real world is starting to take notice in a big way. And finally, we'll look at what's coming next. Okay, let's start with the machines. Because for any of this to be real, you need hardware that is both incredibly powerful and, just as importantly, reliable. And in late 2025, we saw two massive leaps forward on both of those fronts.
First, we've got to get this key idea straight: verifiable quantum advantage. Now, you've probably heard the term quantum supremacy before. That was basically about a quantum computer doing any old calculation faster than a classical one, even if it was a totally useless one. This is different. This is the real deal. It's about solving a useful problem, proving the answer is correct, and doing it faster than any supercomputer on Earth. This is the moment a quantum computer stops being just a cool lab experiment and becomes a powerful scientific tool.
And then, bam, in October 2025, Google's Quantum AI Lab announced they did it. Using their processor, which they call Willow, they achieved the world's first ever verifiable quantum advantage. They solved a problem that's directly related to studying molecular structures. This wasn't just another benchmark, you guys. This was a fundamental shift. And the performance gap, it's just staggering. The calculation ran 13,000 times faster than it would on a top-of-the-line supercomputer. We're not talking about something being twice as fast or even 10 times as fast. A speedup of this size literally puts problems that were once impossible squarely into the realm of the possible. But look, incredible speed means absolutely nothing if your calculations are full of errors. And quantum bits, or qubits, they are notoriously fragile things. They are so prone to making mistakes. So, for a long time, this has been the holy grail of quantum hardware, making them both incredibly fast and incredibly precise. And that brings us to the second major hardware breakthrough.
At almost the exact same time, a company called IonQ announced a new world record for accuracy, or what's called fidelity. They hit 99.99%, what people in the field call 4 nines fidelity. Now, I know that might not sound like a huge jump from the old record, but trust me, in the world of quantum engineering, going from 3 nines to 4 is an enormous leap. It's a game changer because it drastically reduces the work needed to correct errors, making truly reliable, fault-tolerant quantum computers a much closer reality.
So, how'd they pull it off? Well, the old method, which you see on the left, involved these super complex, finely tuned lasers. It was delicate stuff. IonQ's new method uses precision electronics built on standard silicon, kind of like the chips that are in your phone right now. This is a huge deal because it means they can potentially manufacture quantum components using existing factory technology that we know how to scale, instead of building everything as a one-off custom experiment. So the machines are getting faster and they're getting more accurate. Awesome. But that's really only half the story. You also need the software, the code, to control them, to correct their constant mistakes, and maybe most importantly, to make them usable by people who aren't, quantum physicists. Okay, so a huge bottleneck in quantum has always been error correction. See, qubits make mistakes so fast that you need a normal computer basically babysitting them, finding and fixing errors in real time. If that normal computer can't keep up, the whole thing just falls apart. Well, a team at IBM just solved this, and they did it a year ahead of schedule. They created a new algorithm that runs on a standard chip and is 10 times faster than it needs to be. This proves you can build a practical quantum system using affordable, off-the-shelf parts with just fantastic needs. At the same time, the tools we use to actually program these machines are getting way simpler. Think of it like this. Early computer pioneers had to understand the physics of every single transistor to get anything done. Now, you can just write code in Python. New languages and toolkits are doing the same thing for quantum. They're hiding all the crazy complexity so developers can focus on solving problems, not quantum mechanics. This opens the door for a much bigger community of programmers to finally start building things. Okay, so the hardware is better, the software is smarter. This is the point where the real world and the real money starts to pay very, very close attention. And in late 2025, the financial commitments became just impossible to ignore.
First, we saw a major infrastructure investment. D-Wave teamed up with a group in Italy to build Europe's largest quantum hub, backed by 10 million euros. And this isn't just another lab. It's a center designed to give scientists and businesses all across Europe direct access to quantum hardware, so they can start solving real-world problems.
But then we saw a number that just puts everything else into perspective. JP Morgan Chase announced a massive 10-year initiative for security and resiliency. And the price tag? $1.5 trillion.
Now, the crucial part here is why they're making this insane investment. A major chunk of it is targeted directly at quantum computing. They see it as absolutely essential for the future of cybersecurity, for financial modeling, for optimizing portfolios. I mean, when one of the biggest banks in the world bets this heavily on a technology, it sends a crystal clear signal. The era of quantum computing is coming a lot faster than anyone expected.
So you put it all together, these breakthroughs in hardware and software and this massive influx of investment, and it has created this incredible momentum. And because of that, the industry is now able to build a much clearer consensus roadmap for what the next few years are actually going to look like.
And the roadmap is getting really clear. As soon as 2026, we expect to see quantum advantage shown in even more practical, real-world applications. Then, just a few years later, by 2028, the goal is to have utility-scale machines with thousands of powerful logical qubits. And by 2029, IBM's super ambitious Starling system is slated to come online. Look, these aren't just vague hopes anymore. They're concrete engineering milestones.
So the quantum tipping point, it isn't some event way off in the future. It's happening right now. The first domino has fallen, and what comes next is going to redefine technology as we know it. To follow this story as it unfolds, make sure you're subscribed right here to Nexus Tech. And that leaves us with one final fascinating question. For decades, we've had this whole list of problems that were just simply too complex for any computer on Earth to solve. From designing new medicines and new materials to understanding the deepest mysteries of the universe. With these machines finally truly coming online, which of those impossible problems are we going to solve first?